So previously we have worked with the derivation of the displacement as a function of time, as well as velocity as a function of time and acceleration as a function of time. And we have found out that the displacement as a function of time is expressed as a, and then the cosine of omega t plus the phase angle phi. And for our velocity as a function of time, which is simply the derivative, you take the derivative with respect to time of the displacement and you get the velocity as a function of time. And we have found out that that equates to negative a omega and then the sine of omega t plus phi. And so is the process done on the acceleration as a function of time. So you simply take the derivative with respect to time, so you will get negative a, and so you have omega squared cosine of omega t plus phi. And as we have noted in the class, we define for our class, we call this three important variables which are common in this equation. So we have the amplitude, the omega, and the phi as our three kings. So we call this our three kings. So we have to find for these three variables whenever we are given or we are asked to find for the equation. It could be displacement as a function of time, velocity, or acceleration as a function of time. And previously, we have worked already with um, finding for the phase angle phi in our class, and omega is very simple to find. So I know you can remember that omega is simply 2 pi f, so there is not much to do or not much worry about finding for omega. You could find it by this one, 2 pi f, or it could be if you're working with springs, so that's just k over m. So in this session, we are going to find for A. So how do we find for A? So that is our goal in today's session. Okay, now for solving for A, what we are going to do is we start with an expression. So of velocity is a function of time. So from that, we have velocity as a function of time is given by negative A omega and then the sine of omega t plus phi. And this is for cases where our time is set as t is equal to 0. That means that our initial displacement is set also as at x naught, and our um, initial velocity is v naught, which happens to be in x in this case. Or for we are solving for cases in which it's moving on the x. Okay, so what is going to happen here is that from our expression of velocity as a function of time, your t is equal to t naught, or in this case it's equal to 0. So that means that this term here as part of the um, angle omega t, so the time is just 0, so this will be 0. That means that what is left inside our um, sine angle would be negative a omega and then the sine of phi alone. So this is what remains since time t is 0, and then our v here will substitute it with v naught x. So the next thing that we are going to do is we are going to, since we are finding for a and we want to isolate a in either side of the equation. So what we are going to do next is we are going to divide both sides by omega. So what happens when we divide omega? So of course omega on the right hand side would cancel out. So we are left then to work with v naught x divided by omega. And then we have on the right hand side negative a and then the sine of phi. Okay, so this one, a sine of phi. Now, I would like to remind again that our goal is to find for the amplitude A in this case. So what we are going to do next on this one is we are going to square both sides. Okay, squaring both sides would yield us with this result. So we will have v naught x, since this is velocity on x, squared divided by omega squared, and the right hand side we will have what happens on the right hand side is we will have, okay, this will be positive now, it's a squared, and then we have the sine of squared phi. Okay, so that is what we end up when we square both sides. So the next thing for us to do is we will try to add x naught squared both sides. So what happens if we add x naught squared both sides is on the left hand side we have v naught squared divided by omega squared, and then we add plus x naught squared. So we actually intend to do this for us to get rid of the sine. So you will see later how does this get rid of the sine theta, I sine phi here. So you have a squared sine squared phi, and then plus the x naught squared. So as I've said, we want to get rid of this sine function here. So we see sine, the sine, the sine. So we did that by adding the x naught squared. Now you might be asking, how in the world did that get rid of the sine function here? Now if you can recall, I will just change it to green. If you can recall this expression, I'll write it here. The position, or I mean the displacement as a function of time, is actually given to be a cosine. So I have written it already, omega t, and then you add phi. Okay, omega t, and then you add phi. Now, what happens here is that since we are dealing with time t is equal to 0, and that is referring to t is equal to 0, and x is equal to x naught, v is equal to v naught, that means that this x is a function of time, that will be x naught, and then you copy acceleration, and then the cosine, and there is something interesting that will happen here. So the same with what happened in this portion, that will also happen here, because you set the time equal to 0. So what happens is omega times 0, so that will just cancel out, that will be 0. That means that you are left with phi as your angle of cosine. So when you square that, you square x naught, what will be the result is that you will have a squared and then the cosine of squared phi. Okay, so right now I probably am believing that you have seen how much this helps, or how this achieves the purpose of getting rid of the sine, such that we can only have amplitude A. So let's copy what is on the left hand side. So we have v naught excuse me, squared divided by omega squared plus the x naught squared is equal to, we have a squared, and then the sine squared, oh, the squared, sine squared phi, and then you add this term x naught squared. So you have found out that x naught squared is a squared cosine squared theta. So you add that plus a squared cosine of squared phi. Okay, so let's do some algebra here. Omega squared plus x naught squared. So there is something interesting that is going on with our right hand side of the equation. So as you can see, a squared is common both terms. So that means we can factor out a squared here, have a squared, and then what is left would be the sine squared of phi plus the cosine squared of phi. Okay? So, if you remember in your algebra, I mean in your trigonometry class, this is actually a trigonometric identity that equals to 1. Sine squared phi plus cosine squared phi, that is just 1. That means that we have been successful in our goal of isolating A, because this is what we desire to find in the first place. But since that is still squared, so what we're going to do is we take the square root both sides. So yeah, take the square root both sides. So what happens is that, of course, the radical sign would be eliminated on A since they have the same index and power. So what happens is that your amplitude A is now equal to the square root of v naught x, meaning the initial velocity at time t is equal to 0, and then your omega squared, your angular frequency, plus x naught squared. Your initial position at time t is equal to 0 squared. So this is our equation for amplitude whenever we solve for cases in simple harmonic motion where we set the time t is equal to 0, or the initial instant. So if you have questions regarding this one, you can raise your questions in the class or drop it on the comment section below.